Now, at the end of the second step in the process of solution for Van de Heat equation type 5, we reached to something like this. We concluded that u of x and t has to be equal to a constant plus the summation of lots of exponential times cosine and exponential times sine functions, right? This was our conclusion. Now, in step 3, as usual, the thing that we need to do is to find out the value of a0 and an and bn using the initial condition that is given to us, right? Now, in Van de Heat equation type 5, going through the third step is a little bit more tricky because here we have both coefficients of sine terms and coefficients of cosine terms, plus we have a constant a0 that we need to deal with. Now, look, what should we do as a first step? We have to put in 0 instead of t and equate the resulting equation with f of x, right? If we put in 0 instead of t in the previous equation, all the exponential terms are going to disappear because their value is going to become equal to 1, and we're going to reach to this. Now, we have to take care of a0 first. But how do we do that? It is not actually very difficult. If we integrate both sides of this equation with respect to x from minus L to L, which is the domain of x for Van de Heat equation type 5, then we're going to have this equation 114 that you see, right? We're going to have this. But the good news is that all of the integration of sine and cosine terms into the sigma are going to turn out to be 0. And you can verify this on your own. All of these are going to turn out to be 0 for all the values of n, no matter what. All of these are going to become 0. So we're going to have integration from minus L to L of a0 equal to integration from minus L to L of f of x, right? The first integration is a0 times 2L, and the second one depends on the specific f of x function that we are given. So a0 is going to become equal to 1 over 2L times minus L to the integration from minus L to L of f of x dx, right? So a0 is determined. Now, in order to determine an and bn, we have to do something similar to what we did for the previous cases. In order to determine an, we have to multiply both sides of this equation to cosine of n pi over L x, and then integrate. And in order to determine bn, we have to multiply both sides of this equation to sine of n pi over L x, and then integrate. And you have to pay attention that in Van de Heat equation type 5, the domain for x is from minus L to L, right? You have to be careful about that when you're doing the integration. Now, for determination of an, after multiplying both sides by cosine of n pi over Lx and then integrating over the domain from minus L to L, we're going to reach to this equation that you're seeing. Now, in this equation, into the sigma, all these integrals that are sine times cosine are going to turn out to be 0. Now, this integral also is going to turn out to be 0 for every value of every positive integer value of m. Now, the only integral that can be equal to something non-zero is this integral, and in one specific case, and that specific case is when m is equal to n, right? So we're going to have an integration from minus L to L of cosine 2 of m pi over Lx, and the result is going to be the integration from minus L to L of f of x cosine of m pi over Lx dx, right? And from this, we can conclude that an is equal to what? Is equal to 1 over L, not 2 over L, like the previous cases. 1 over L, integration from minus L to L of f of x cosine of m pi over Lx dx. Why is that? That is because the integration from minus L to L of cosine 2 dx is equal to what? Is equal to 1 over 2 times L minus L, which is 1 over 2 times 2L, which is L, right? Now, for Bn, we go to a very similar process, but this time we multiply both sides by sine and integrate over the domain from minus L to L, and we're going to reach to this. 1 over L integration from minus L to L of f of x sine of m pi over Lx dx. Yes? Now, in summary, the solution to our 1D heat equation type 5 became this. This is our unknown function, and the coefficients are given by these equations. Yes? Questions? Okay. Guys, you know that after some discussions with the department, we came to the conclusion that record the videos for the classes. And Farhad, what are you doing? You're causing a lot of noise, Farhad. Now, after some discussions with the department, we came to the conclusion that to record the classes and send it to you before the class starts, then you have to watch the recording online, and the online session that we're gonna have at the specified time each week is gonna be dedicated to the Q&A sessions. Okay, so we're gonna have just Q&A in the online sessions that we're gonna have. You see that previous year's students did actually have quizzes. and they weren't just eating and sleeping like you. Interesting, huh? Yes. Now, this was their first quiz, and we actually had three quizzes in that specific semester that I'm talking about. Now, the question says the temperature distribution U of x and t at any time in a metal rod of 2 centimeters long is described with PDE and boundary conditions as seen below, right? This is your PDE, and these are your boundary conditions. Now, by looking at the boundary conditions, that you see that exactly we have a type 3 yes, yes, exactly. Very good. Yeah. How can we know? How can you know what? Exactly. Muhammad has answered you by looking at the boundary conditions. At the beginning, we have the Dirichlet, and at the end, we have Neumann. So this is type 3, right? You have to be very careful not to mix it up with type 4. In type 4, in the beginning of the metal rod, we have Neumann, and at the end, we have Dirichlet, right? Now, this is a 1D heat equation type 3, okay? Now, part A says solve the PDE above with the given boundary conditions. If initial temperature is given by a general function like f of x. Hmm? So, you see that the boundary conditions are given in this setup, but the initial condition is not. And there is a reason behind that. Part A says consider the initial condition u at x and 0 to be equal to a general function like f of x. And part B says if f of x is equal to this specific function, then it says determine approximately how long does it take for the temperature at point x equal to 1 centimeters, middle of the metal rod, to drop to 1 degrees Celsius, right? Now, let's go to the actual solution. When you're going through the solution and writing the steps, keep in mind that for this specific case, alpha is equal to what? Alpha is equal to exactly Lana. Exactly Lana, thank you. And L is equal to L is equal L also is equal to 2. Yes. So let's get down to the solution. Now, now in this solution, in the beginning, we said that alpha is equal to 2 and L is equal to 2. And we were writing, and when we were writing the steps, we just put in alpha and L, knowing that the values is equal to 2 and 2. So we start by the first step, the assumption of separation of variables. We reach to these two ODEs, and at the beginning, this is all of step 1. All of step 1 is summarized in this one line. For step 2, just as usual. Binai, are you listening?
Yes, sir.
Good. Just as usual, we translate our boundary conditions to conditions in terms of if, and we get if at 0 equal to 0 and if prime at L equal to 0, right? And Binai, for your information, all of it, all of the things that you see on your lecture notes and on everything else that I give you is something that I've written. I've previously written that with my own hands, with these hands, if you see
And the
them.
pictures were written on by hand, you know?
Yeah, you should. So, yeah. Now,
Yes.
if lambda is negative, then here we have the luxury to go through this quick process. We can jump to G and say that as long as G can't go to infinity when T goes to infinity, then then alpha can't be negative. But you're going to see that in wave equations, for the case where lambda is negative, you don't have this luxury. Now, when lambda is equal to 0, then just like before, f double prime is equal to 0, and we're going to conclude that because of the boundary conditions in terms of f is going to become 0, which is something that we can't tolerate. So lambda can't be equal to 0 again. For lambda positive, we go through the same process. These are all the stuff that you've learned when we were working on 1D ET equation type 3. Now, at the end we conclude this, right? Now, for L equal to 2, n minus 1 over 2 pi over 2 to the 2 is going to become equal to what? It is equal to 2n minus 1 over 4, right? This is equal to 2n minus 1 over 4 times pi, all of it, to the 2. Now, we determine f of x just like usual. Then for this specific lambda, we determine g of t also, right? And determination of u and using the superposition. When it comes to finding Cn, we use the initial condition that part A gives us, which is for a general f of x. And we find Cn to be equal to this. We avoid writing all the multiplication and integration steps. Okay? But when you're not sure, actually you have to do that in your mind. You have to do it, you have to do some calculations on your mind and then include the result here. But you have to know how this result is achieved, because in some cases you're not sure what the Cn is going to be. And in those times you have to do the calculations anyway. So you have to know how do we reach to these formulas for the coefficients in the third step. So guys, less than 1 minute is left from this Zoom meeting. So we're gonna stop at this point. I'm going to send you another link and be back after 5 minutes of rest. Okay? Yes?
Yes.
Very good. So guys, we solved part A of this example. The part B is a little bit more tricky. It look, it says if f of x is equal to 5 times sine of pi x over 4, then determine approximately how long does it take for the temperature at point x equal to 1 centimeters, which is the middle of the metal rod, to drop to 1 degrees Celsius. Now, the solution to part B has two parts. First, we need to calculate the actual u of x and t for this specific f of x that is given to us. And then we're going to be able to determine how long does it take for temperature at this point to become equal to this value. Okay? So, let's get to it. Now, we're going to utilize the conclusion that we made at the end of the solution to part A. And it was this. We found out u of x and t and Cn. We replace alpha equal to 2 and L equal to 2 into it, and we reach to this. U of x and t is equal to sigma n from 1 to infinity Cn e to the minus 4 times 2n minus 1 pi over 4 to the 2 times t times sine of 2n minus 1 pi over 4 x. And Cn is integration from 0 to 2, because this is equal to L, f of x sine of 2n minus 1 pi over 4 x. The integration with respect to x. Now, in part B, when f of x is equal to 5 times sine of pi x over 4, then Cn becomes equal to integration from 0 to 2 of 5 times sine of pi x over 4 sine of 2n minus 1 pi over 4x with respect to x. And we know that this value is equal to 5 when n is equal to 1. This part is very tricky. You have to be careful not to make a mistake here. And Cn is going to be equal to 0 when n is not equal to 1. Guys, you have to have some questions at this point. Binai, wake up and ask some questions.
Sir, I'm wide awake, but I don't have any questions.
So you exactly know what is going on, right?
A general idea, but the steps I cannot follow.
Okay, so let me emphasize here. Please pay close attention because this is very important when it comes to solving the actual examples. Now, why did we say for n equal to 1, we're going to have a value, and for n not equal to 1, we're going to have 0? Because, look, here we have sine of pi x over 4. So, and here we have sine of pi x over 4 times 2n minus 1. When these two signs have the same argument, meaning what is going on inside of the parentheses, have the same argument, then the value of this integration is not going to be equal to 0. And the value of the integration, as you learned, is going to be equal to half the length of integration, meaning 2 over 2, which is 1. But when these two signs are different, which is going to happen for every value of n that is not equal to 1, then the result of the integration is going to be 0. So, for n equal to 1, this sign becomes sine of pi x over 4, and the result of the integration is going to become 5 times 2 over 2, which is 5. Yes? And for all the other values of n, the result of the integration is going to become 0.
So can I ask you a question?
Very well. Yes, go ahead.
Say for all cases, for the value of the n, you should say a number that's both of them are going to be the same. You mean like that? I mean here's sine pi x. You mean you will set n a number that another sign is also gonna be sine pi x over 5.
Look, we had a rule for integration of the multiplication of two signs. Do you remember that? The rule said integration over one period of or integration from 0 to L of sine of n pi over L x sine of m pi over L x dx is equal to 0 when m is not equal to n, and is equal to L over 2 when m is equal to n. Yes? Did you understand that, or
Yeah, I remember that, sir.
yeah? We are using exactly the same rule here. The value of this integration is equal to L over 2, which is 2 over 2, when these two arguments are equal. When these two arguments become equal, when n is equal to 1. Yes?
Yes, sir.
Absolutely understood, or you have doubts?
No, I understand.
Very good. No problem. Now, Muhammad Abdul Razzaq, go ahead.
Have the same equation.
Mhm.
For all cases, the value should be same. For example, the sine of pi over 4x, and another should be a sine of pi over 4x.
No, for this, if we want to use that general formula that we had, yes, you have to understand the concept. For example, if f of x was equal to x, then this stuff would be useless. Then you had to calculate you had to use, what was the name? You have to do integration. You had to do integration by parts. Yes? If f of x was equal to x, you had to do integration by parts. Right? Muhammad, are you hearing me? Now, this is a very important conclusion that we have made. By this, we know that only C1 has a value and it is equal to 5, and the rest of the C's are equal to 0. So, u of x and t, look at it. U of x and t was equal to this. Now, for this specific f of x, all of its coefficients are 0 except for C1. So u of x and t is equal to C1, which is 5 times e to the minus 4 times 2 times 1 minus 1 pi over 4 to the 2, which is pi over 4 to the 2 times t times sine of 2 times 1 minus 1 pi times x, which is sine of pi over 4x. Right? So u of x and t is equal to this. Now, after finding u of x and t, most of the job is done, but our job is not over. The question says, how long does it take for the temperature at the middle of the metal rod, which is the point x equal to 1 centimeters, to drop to 1 degrees Celsius, right? So we want to find the t that u at 1 and t, which is equal to this, becomes equal to 1. Now if we simplify this term, we're going to get 5 times e to the minus pi 2 over 4 t times the square root of 2 over 2, right? Now we have to solve this equation. We have to solve this equation to find t. How do we do that? We say e to the minus, we strip this exponential term and move everything else to the other side. We're going to get e to the minus pi 2 over 4 times t equal to 2 times 2 over 5 times a square root of 2. So, using our knowledge, our basic mathematical knowledge, we can say that this exponent minus pi 2 over 4t has to be equal to ln of 2 over 5 times the square root of 2, right? And from this, we can say t has to be equal to minus 4 over pi 2 ln of a square root of 2 over 5. And if you use a calculator to make some simplifications, this t is equal to 0.51 seconds. So in half of a second, the temperature in the middle of the metal rod drops to 1 degrees Celsius. Understood? Guys, are you with me? Hassan, is it clear what is going on? Guys, let me tell you, Analysis 2 is the most difficult math course that you've ever had. Okay? It is difficult for...
in the worst situation.
Yes, in the worst situation imaginable. That is the difficulty of this subject of math, is something that all the engineers all around the world complain about. So This is something natural and you have to put in some time into it. You have to study the lecture notes that I send you. And I've prepared them with a lot of pain. This stuff is included in no textbook. No textbook uh, gives this stuff very clearly. So please read the lecture notes that you're supposed to read and try to stay with the class. Try to uh, be up to date with the class. Now, this was one quiz for the previous year's students. Now, let us go to their second quiz. I'm going to share my screen with you. So, guys, do you see this? Now, this question is a little bit easier. Actually, it is easier in comparison to the previous question. And you are lucky. Here also, the PDE that you have is a PDE of which type?
Also type 3, I think.
Exactly, Lana. Where are the rest of you guys? Asu, what is the value of L here? Asu. Asu is absent, huh? So Asu, what is the value of L here in this example? Exactly. What is the value of alpha? What is the value of alpha? Binoy, what is the value of alpha?
I guess 1.
Yes. And f of x in this specific case is equal to x. So the question is, it says apply the method of separation of variables to determine the solution of this 1D heat equation with the following mixed boundary conditions. Okay? Boundary conditions are given to you. And sorry, in here we have to have round over round x of u at pi and t. This u is missing here. But you understand that. Now, by knowing that alpha is equal to 1 and L is equal to pi, we start solving the question. Step 1 is just routine. At the end of it, by knowing that alpha is equal to 1, we reach to g dot over g of equal to f double prime over f equal to minus lambda. Now, in the step 2, we do the routine and translate our boundary conditions to conditions in terms of f. Okay? We're going to have f at 0 equal to 0 and f prime at pi equal to 0. Now, because it is a 1D heat equation of type 3, we easily conclude that lambda can't be 0, lambda can't be negative, and we go to the case in which lambda has to be positive. Now, f double prime plus lambda f equal to 0 is going to give you f of x equal to c1 cosine of a square root of lambda x plus c2 sine of a square root of lambda x. Now, me highlighting the text is somehow like writing it. Yes? Thank you, Hassan. Shut up, Binai.
No. A big no. With a big O.
Quiet. Now, f at 0 is equal to 0. We replace 0 in the previous equation, and we're going to get c1 cosine of a square root of lambda 0 plus c2 sine of a square root of lambda 0 equal to 0. That means c1 has to be equal to 0. Why? Because cosine of 0 is equal to 1. Sine of 0 is equal to 0. Now, we use the second condition on f. Knowing that c1 is equal to 0, f of x becomes c2 sine of a square root of lambda x. Is it right, Binai?
God knows.
God knows. No, you know. Because c1 is equal to 0, f of x is equal to this, right? Now, f prime is equal to what? c2 square root of lambda cosine of a square root of lambda x, right? And we put in pi instead of x, and we reach to this. Yes? Now, just going through the routine, the square root of lambda is not 0, and if c2 is equal to 0, then u becomes 0, which we try to avoid. Now, cosine of the square root of lambda pi is equal to 0, and that means the square root of lambda pi is equal to n minus 1 over 2 pi, which is going to give you the conclusion that lambda is equal to n minus 1 over 2 to the 2. And that is true for every value of n from 1 to infinity. Every positive integer value of n from 1 to infinity. Now, this is the general. In the general case, we saw that lambda for the 1D heat equation type 3 would be n minus 1 over 2 pi over L to the 2. Now, because L is equal to pi and L in the numerator and denominator cancel out, and lambda becomes this. This is a verification of the correctness of the result that we found here. Right? Now, when lambda is equal to this, f of x, which was c times sine of a square root of lambda x, a square root of this lambda becomes n minus 1 over 2. So f of x becomes this. F of x becomes this. Right? Now, on the other hand, what is it that we have to do here? We have to find g, then we have to find 1u, then we have to use the superposition to find u in the sigma form, and step 2 is going to be over. Then in step 3 we have to use the initial condition to calculate the undetermined constants, right? Now, finding g is not that difficult. G of t is equal to c times e to the minus lambda t. G of t, because lambda is equal to n minus 1 over 2 to the 2, is equal to c times e to the minus n minus 1 to the 2, sorry, n minus 1 over 2 to the 2t. Now, u of x and t, which is the result of the multiplication of f and g, is equal to this, and the summation of all these u's is going to give us this. Questions? Guys, questions? Questions? Very well. Now, in step 3, we have to utilize the initial condition to find Cn, right? Now, u of x and t is equal to this. U of x at 0 is going to become this, and this is equal to x. Now, finding Cn, we have to write Cn times the integration of sine 2 of this dx is equal to integration of x times sine of n minus 1 over 2x dx. So Cn is equal to this. Now I did the calculation in my head and wrote this formula for Cn. Yes. Now the difficult part in this question, the most difficult part is to actually calculate this integral. But it is not that difficult. You have to do integration by parts, which you are perfectly able to. Now, if you do that, after some headache, the final result becomes this. And for various values of n, you're gonna have 8 over pi for n equal to 1, minus 8 over 9 pi for n equal to 2, and 8 over 25 pi for n equal to 3, and etc., etc. Now, if you rewrite the function u of x and t with this c that you have found, you can put, guys, please pay attention, please pay close attention, look at your screens. You can put this c, the value of Cn, you see that it depends on n. You can put it into this formula that you have found for u and reach to this conclusion. Yes? Do you see how beautiful it is, the result of our calculation? 8 over pi sigma for n from 1 to infinity minus 1 to the n plus 1 over 2n minus 1 to the 2 e to the minus n minus 1 over 2 to the 2t sine of n minus 1 over 2x. A coefficient times an exponential component times a sine component. Yes? And questions? Guys, questions? No? So, there's only 5 minutes left from this session. I'm gonna end the session here, send these two examples to you, and send another link for the continuation of our lecture today after 5 to 10, after, guys, after 20 minutes of rest, 20 or 30 minutes of rest, right? Huh? Let it be over?
Yes.
Guys, no, no, no. No, 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 no. Faster. Now, the recording has started. Now, this is going to be your homework for the next week. Now I'm coming up with examples in the real time so that you can see how you can come up with examples on your own. Now, I wanted to have an example of a 1D heat equation type 1. I considered alpha to be equal to 1, L to be equal to pi, and f of x to be equal to x. And this is the result, right? Now, maybe I want another example. Now, I want to have a 1D heat equation, again type 1, and alpha, I want alpha to be 2. So I write a 4 here. That means alpha is equal to 2. L is still, pi is a good number for L because n pi over L in the solution becomes n, right? Now, instead of f of x equal to x, this time I write sine of 5x. 8 times sine of 5x. Good? You already know the solution. Yes, yes. Now, I want another example of a 1D heat equation type 2. I write this. So alpha, I'm going to consider it to be equal to 3. So I write 9 here. For L, I assume L to be pi over 2, just for some, for the sake of variety. Now, pi over 2. Binai, dear Binai,
Yes, sir.
I'm writing stuff here.
Oh, thanks, God.
Now, I wanted this to be a 1D heat equation type 2. So I should have the derivative of the unknown function at the boundaries, right? So instead of u, I should have ux, right? Now, for the initial condition, if I leave it like this, the smart students now know that with this initial condition, all the c's are going to turn out to be equal to 0. So I change it. N pi over 2, 2nx cosine of 4x. Sine of 4x. cosine of 6x. Oh, beautiful example. Now you see how I'm going to give you questions in your exams. Now, for example, I want to give you a 1D heat equation type 3. What do I do? Guys, this thing that I'm doing here is very useful for your learning. So if you haven't if you haven't paid any attention yet, please at least pay some attention now. This is super important and super necessary. Now, I'm looking for a 1D heat equation type 3. Let us get rid of alpha. Imagine it to be equal to 1. Okay? Lana, are you listening? Now,
Yeah.
pi. Now, I want to leave it as pi over 2. So in this, the eigenfunction, Muhammad Suleiman, in this example, the eigenfunction is going to be equal to what? Can you tell me?
Sorry, I didn't pay attention.
No, just pay attention now.
All right.
We have a 1D heat equation type 3. Alpha is equal to 1. L is equal to pi over 2. The eigenfunction is going to become equal to what? Valid, can you tell me? Oh, oh my God.
Your
Binay.
legends are dying, sir.
No, you are my legend. Binay, you answered
No,
me.
no. Walid was your legend. Asso, Suleiman, all of them are gone. Low battery, dead battery. Dead.
Don't be so happy. Avan is gonna answer me now. Avan knows. Avan, please. Avan, where are you? Avan, you know, you always know. Asu, Asu Gyan, where are you, Asu? Save me from Vinay. Dear Asu, where are you? In the WC. So,
Dead battery.
so be naive one. You guys let me down. Be naive one.
Yes, yes.
Yes. Now, uh, guys, the eigenfunction for this case. Shoresh, Kayvan, Farhad. Oh, really? Let me unmute you. Let me unmute you. Wait. Asu. Where is Asu? Ay برار. As. Hassan, what about you? Do you know the answer?
Nope.
No? Dina, yes, stop laughing, please.
So fun. The nicest class I have ever had.
Oh, I found Asu. I'm gonna unmute him and he's gonna answer. No, yeah, he is. Asu always knows everything.
Oh, I don't know.
Sir, it was the ASO before Corona. The new version of ASO have already changed.
Why did you tell me to unmute you?
Sir, we have changed.
My God.
We are
It is
the
not
new
HIV. It is not HIV. It is just Corona. My God. Now, guys, listen. In this in this example that we're solving, in this example that we are solving, we have a 1D heat equation type 3. How do we know that? By looking at the boundary conditions, right? We have a mixed boundary condition that is equal to 0 or is a Dirichlet type boundary condition in the beginning of the metal rod and is of Neumann type at the end of its domain. Now, the eigenfunction for this specific problem is this. For type 3, the eigenfunction used to be sine of n minus 1 over 2. Guys, do you see what I'm writing? It is small. Now, the eigenfunction for the 1D heat equation type 3 would be this. N minus 1 over 2 pi over L. So for this specific case, case 4, the eigenfunction for L equal to pi over 2 is going to be sine of n minus 2n minus 2n minus 1 pi, right? Muhammad Suleiman, right?
Yes, I think it's right.
Now you should be sure at the moment, right? It is equal to this pi cancels out the other pi, 2 times n, 2n, 2 times 1 over 2, 1. Sorry, I forgot x. Don't do that. Did you see what happened? What? We are trying to solve it. No, what? I'm writing it in Word.
Erdogan is using text.
I'm reading, I'm Erdogan, I'm using Word. Good question, anyway. Any type of question that you have is a good question. Now, I'm using Word, and the conclusion was this, that the eigenfunction for this problem is sine of 2n minus 1 x. Now, I'm using that to give you a good initial condition. Now I write sine of 4 times sine of 7x. Okay? Do you see the magic? Now, we want an example of a 1D heat equation type 4. Now, here, this is your fifth example. I want alpha to be equal to 7. Yes? What the, if alpha is 7 here, you alpha 7 or alpha 2 7? Okay, so here you have 49. Now, actually, we rarely see values of alpha equal to that, but that is Hassan's decision and we respect that. And you're welcome. Now, so Hassan, can you tell me now what is going to be the eigenfunction for this example? As you see, the eigenfunction only depends on the PDE and boundary conditions. It doesn't depend on the initial condition at all. That is a very important point to have in mind. Now, the eigenfunction, which is the function that you find at the end of step 2, right? After finding lambda and finding f of x. Now, for this case, the eigenfunction, can anybody tell me what is it equal to?
Cosine n minus 1 over 2.
Ahsant, Lana. Ahsant. Binay, did you see that?
Yes, sir. After 2 years of taking analysis, she should be.
Oh, you're so rude. This is her first time. This is her first time. I didn't expect that from you. I didn't
Sir,
expect that, Binay.
last year you take analyze as well. See,
Oh, yes, yes. I now I decided not to call her anymore. Oh. That was very ugly. So,
sir, you know what I mean? She studied analyze last year as well.
Binay, I'm gonna mute you.
No, she wasn't there. She didn't take second semester.
Yes, she didn't. So, guys. Now our eigenfunction is equal to this. Cosine of 2n minus 1 x, right? Because L is equal to pi over 2. Now, if L was equal to pi, what would happen? Can anybody answer me? Answer me, Muhammad Abdurazzaq. Can you answer me now? If L was equal to pi instead of pi over 2, then for this example, the eigenfunction would be guys, do you hear me?
Yes. Cosine
Go ahead.
n minus 1 over 2 x.
Ahsant, exactly. Thank you so much. Now, 5 times. Now, for the initial condition has nothing to do with the eigenfunction, but I'm setting it up in a way that at the in step 3, you're gonna find something good, neat and tidy as the result of your calculations for Cn. Okay? So I'm gonna give you cosine of 9x. 2 times cosine of 9x. Okay? What? No, it makes differences. Ardavan, can you speak a little bit louder? But I'm hearing you. Yeah, can you repeat yourself, Ardavan? No, even if here I write sine, the eigenfunction still is cosine of 2n minus 1x. Fourth type, actually. This one, yes. The eigenfunction that we find, Ardavan, only depends on the boundary conditions. Yes. Yeah, very good. But here I give you cosine so that you get a good result for Cn in step 3. If here I wrote sine for the initial condition, then all the c's in the step 3 would be equal to 0. Yes? Now, we want another example, this time for a 1D heat equation type 5, and that would be enough. Okay? One example from each type, and that would be enough. But guys, in your exams, I'm not going to tell you what type the equation that you have is, right? I'm not going to tell you the type. So you have to recognize that on your own. Now, for the boundary conditions, let's this time include pi. Okay. Oh, sorry. We have to change this. Minus pi guys, are you awake? Jihan, where are you? Let's check on Jihan to see if she's awake. Jihan is asleep. Havan, where are you? So, guys, please pay close attention. Now, in case 6, we have a 1D heat equation type 5, right? Avan, yes? Now, what is the eigenfunction for this? For a 1D heat equation type 5, we have two eigenfunctions, right? Now, one eigenfunction is in the form of sine of n pi over Lx, and the other eigenfunction is in the form of cosine of n pi over Lx. Yes, guys, this is very important. So the eigenfunctions are cosine of nx and sine of nx. Yes?
Yes.
Very good. Now, so I'm going to give you this initial condition. 5 times. Hassan, you tell me
What?
the initial condition. It has to be in the form of sine of nx and cosine of nx.
I know.
Not two, so 2 times cosine of 9x plus 5 times sine of
3x.
3x. Very good. 3x. So guys, these are your examples. This is your homework. I am gonna send it to you right now. For the next week, you have to solve these 6 questions. And when you want to send me your answers, how do you do that? You write your answers on a piece of paper. Guys, are you listening to me? You write your answers on a piece of paper and use your cell phone, take a picture of it using the software. There's an app called Cam Scanner. Huh?
Yeah.
Let me. Are you familiar with that app?
Yes. Very good.
Why we don't use the normal one? Is it problem?
Because you're gonna have lots of pages. If you don't use Cam Scanner and uh, don't
So Adobe
create
Scanner
a
is better.
what?
Adobe Scanner.
Maybe you can use that also.
Yes, Adobe Scanner is better.
Very well. I am more used to Cam Scanner. But anyway, I need a PDF file. That is the point. Any software you can use. Cam Scanner is just a suggestion. Create a PDF file of your handwritings. Absolutely write your name on the PDF file. Just don't just send me a PDF file with a screwed up name, because I have lots of PDF files. You absolutely have to write your name and the number of your stage on the PDF file, please. And it is better, I think, to for all of you to send your PDF files to Mr. Hassan, so that Mr. Hassan can collect them and put them into a zip folder and send me the zip folder. Okay, guys? Okay, Mr. Hassan?
Okay. Okay.
Thank you guys very much.
Hussein,
What?
please for this homework, we should solve all of the steps. For example, some steps maybe we know that it's not
I
possible
know,
how.
I know. But when you're writing your solutions, uh, look at the solution to these quizzes that I sent you. Okay? Adopt the same manner of writing. Okay? Maybe some steps are trivial, but that is just a routine. You can write those steps faster. Huh? So that is it for today, guys. Thank you for your patience. Thank you for your cooperation. And if you have any questions now, I'm at your service now.
Thank you very much.
No problem, guys. Thank you all, and goodbye for now. If you have any questions about the course or anything, you can contact me on Telegram or via email. Thank you all very much. Goodbye till the next week.
Goodbye.
Goodbye.